SwayamPrabha. Digital India. Educated India.
Hello everyone, today I am going to deliver a lecture on analysis of eccentrically loaded welded joint. See, this is the content of today's lecture. First of all, I will discuss how to analyze a eccentrically loaded welded joint. After that, I will solve some problem based on this eccentrically loaded welded joint. Eccentrically load in the plane of welds can be described in the following way. Let us consider a bracket, you can say, this is a bracket which I am interested to connect with another plate. This is another plate. So, this bracket I am representing 1 and this is another supporting plate 2. Over this, generally once I go for connecting these two components, what are the thing required to do? You have to do some welding operation. So, here I am showing the welding which I made for connecting this bracket, that means this bracket, this is called bracket, you can say bracket. So, it is I am connecting by using welding over another plate or another support, that is I am representing by 2. So, for connecting this bracket over another plate, what are the thing required to do? You have to do some welding operation. Here let us consider 2 welding is required to connect this bracket with this supporting plate, you can say. So, what should be the dimension, or you can say what should be the parameters required to connect this bracket over another plate, that we are going to find out in today's lecture. That means the design of welded joint subjected to an eccentrical load in the plane of weld consists of calculation of primary and secondary shear stresses. So, here I have already told a bracket which is subjected to a eccentric load. Here you can see this eccentric load is P. This eccentric load, and it is attached to the supports by means of 2 parallel weld. Two parallel weld, this is weld 1 and this is weld 2, you can say. This weld 1 and 2 I am representing in terms of W1 and W2. So, here we have to design what should be the dimension of these welds. That means, here always you should keep it in mind, to design a weld joint, first of all we should know what should be the dimension of that weld. What do we mean by dimension of weld? Dimension of weld means to find out, you can say, leg length and you can say throat size. So, we have to design to support a plate over another support, you see, you can see here. So, what should be the size of that weld? Size of this weld means what should be the throat side or what should be the leg length. Now, in previous case what we have observed that if the weld is transverse plate or parallel plate, there we have seen generally we have already considered throat size is dependent on leg length, where leg length we consider the thickness of the plate. So, they are generally in case of parallel and transverse types of plate welding cases, we have designed like that. From there we observe that how to find out the length of the weld required to support that mass of load, if it is subjected to transverse types of load or parallel types of load. Now, here it is not a transverse or parallel types of load, you can say. Here this load, instead of transverse or parallel type, here this load is eccentric in nature. Eccentric in the sense, it is generally, instead of passing through the CG of that weld, you can say, it is passing through some eccentric distance from that weld. That means, it is subjected to some load which is away from the weld region. So, once this load and weld lie in same plane, here you can say this weld as well as this load is lying on this bracket itself and same plane, you can say. that is called plane of weld subjected to eccentric load. That is why this types of analysis is called eccentric load in the plane of weld. What I am telling, understand? Now, here we have given the length of weld. So, if we have given the length of weld, then what happens? What should be its size? So, in previous case we have already familiar with, that means in previous analysis we already know that what is the throat thickness, what is the leg length. So, there we just find out the length of the weld, but in this case here let us consider the length is given. So, we have to find out what should be the throat thickness or leg length. So, this is our design consideration here. So, to find out these things, actually detailed steps I will discuss in this lecture. So, to find out the what it is called leg length or throat thickness, here we have to follow some standard steps, you can say. This standard steps, here the first step is to find out the CG of the weld which we are using to connect the bracket with support, you can say support in the sense like this support plate is I am representing by 1. Okay. So, let us here we consider two parallel weld, here we are putting weld 1 W1 and W2. So, for this weld W1 and W2, what should be the throat thickness and what should be the leg length? To find out this thing, what are the different steps we have to use, that I will now going to discuss in details. So, here let us, this length of the weld is given, length is L, and let us the throat thickness we have to find out is T, which we have to find out. So, for finding out these things, here already I have told you this bracket is subjected to a load P. So, you see, to support this eccentric load, why it is called eccentric load? Because this load is not passing through the CG of all weld, as it has a distance from the CG, you can say let the CG is representing as G. So, it is eccentrically placed, this load is eccentrically placed. So, this is the distance I am representing in terms of E here. So, distance from CG and the loading position here I am representing in terms of O, let us. So, GO, this is the eccentric distance, is E, this is called eccentric distance, eccentric distance. So, here P is also given, but this eccentric distance E we have to find out. How we can find out this eccentric distance, that I will now discuss in detail in subsequent slide. So, first of all the step which we have to follow for finding out the throat thickness, first and foremost thing is to find out primary and secondary shear stresses. After that, based on this primary and secondary shear stresses, we have to find out the throat thickness. Now, how to find out this primary and secondary shear stresses, that I will discuss first. After that, actually I will show how to find out this throat thickness. So, the first step here to find out this primary and secondary shear stress, first step is to find out the center of gravity of wall welds. This you should keep it in mind. Here we consider, let us two different weld, that is weld 1 and weld 2. So, for this weld 1 and weld 2, we have to find out what is the G. What is the G? G position, how to find out the G position? That is very simple steps, you know. Let us consider this is our y axis and let this is our x axis. So, x and y axis is known. So, with respect to x and y axis, here one weld is there, here one weld is there, here we consider two weld, that is why we are considering two different weld. So, this weld length is given, Now, here generally to find out the CG, here we can consider this weld thickness as unity. That is why here this weld is treating as a line, that which I have written. So, this is one assumption you can say. So, here we generally consider this is our, this is our x, this is our y axis and this is our x axis. So, with this y axis generally we can easily find out what is the CG. So, to find out the CG we generally use principle of first moment of area, that you can say. What is principle of first moment of area? Principle of first moment of area is, this weld area is A1, this weld area is A2. This weld area is A1, A2. What does it means? Here let us consider the throat thickness we are considering as T. So, always you should keep it in mind, generally in throat thickness position the weld is failed, because in throat thickness position we get minimum cross section. That is why I have already discussed in previous lecture also. That is why in our analysis also we will consider the throat thickness as the minimum cross section where the failure will occur. So, based on this throat thickness only we will find out the area. So, here what is the area A1? So, area A1 is equal to your L into T. Similarly, area A2 will be your L into T, because here both the weld we consider as same length. If it is different, then we can consider different length. Now, with respect to Y, we know the CG of this what it is called weld 2 is L by 2. Similarly, with respect to Y, the CG of this weld also L by 2. Okay. So, we can easily find out what is the overall CG with respect to y axis, that is x bar. X bar, once we take with respect to y axis, there we can get x bar will be equal to your what we can say moment of sum equal to summation of moment. These things we can use. So, what we can write? So, first moment of area of first weld will be your A1 into L by 2 plus first moment of area of second weld is equal to A2 into L by 2 divided by, you can write as A1 plus A2. So, this is actually sum of moment equal to moment of sum. So, moment of sum is this one, 2 moment we sum, and sum of moment is generally x bar into total area, you can say. So, by this we can easily find out what is x bar. Similarly, y bar also we can easily find out what is y bar. So, y bar, to find out y bar, generally here you can see as this x axis is passing through what it is called the second weld. So, y bar we can directly find out like this. Y bar will be generally we can find out like here A1, the distance of CG from this is also given. Let us from here to here distance is given, let us B breadth. So, here generally this we can easily find out. So, A1 into you can say B, and here as this x axis is passing center of this first weld. So, here you only consider A1 into B divided by you can say A1 plus A2. So, what will be the things as A1 and A2 are same. So, you can say this will be your B by 2, because here you can say the distance of A2 into 0, because it is passing through is CG, x axis we consider let us is passing through is CG. Okay. So, here you can say y bar is B by 2, that is way we can find out here this G. Now, if instead of 2 weld, if there is some other weld like let us here another weld is also there. So, if this weld will be there, that case also we can easily find out what is the G. So, first and foremost thing is to find out the CG of all weld. This step you should keep it in mind. So, how to find out this CG of all weld? This I have already shown. You have to find out CG of all welds. You need not to find out the CG of the plate. You have to find out CG of all weld. So, to find out the CG of all weld, what we consider? We consider the weld as a line. There we consider only the throat thickness. So, because compared to thickness of this weld, here length is very high, that is why here we treat weld as a line. So, once we find out the CG, then we can easily find out what is the distance between CG and position of this eccentric load P. So, this second step is to find out the distance between G and position of load E. So, that things only I have written. So, suppose G is the center of gravity of two wells here which we consider, and E is the eccentricity between the center of gravity and the line of action of load or force P. So, we can easily find out what is the distance E. So, this distance E we find out by using this concept. That means, first of all we have to find out the CG of all well, and we know the position of P. So, distance between G and position of load P is the eccentric distance. After that, this third step is to replace this load P, replace this load P to CG. So, let us consider this is a beam, you can say, or any types of a structure. Now, let this is P. Now, let us this P we want to shift to another place. Let us in this in location 1 we want to shift this P. So, to shift this P to location A, or you can say location 1, there is a principle that is called principle of applied mechanics. What does it tells? Once we shift this P to here, then what happens? Let us here we apply a similar load P in this position P, and if there we apply a similar and opposite force P in that same location, then in this location A, summation of this two force, you can say summation of these two force will be 0, correct. So, let us consider we apply a force P which is similar to this externally applied load P, and opposite direction also we apply another force P here. Okay. Now, in this new location 1, due to this application of P and P, it will be nullified, because you see in this position A, due to this equal and opposite force, it will be nullified, that resultant force is 0, you can say. Now, we will consider this opposite force and this opposite force. This will create a couple. If we take moment, about this location 1, this couple will be how? This couple will be just, we know what is couple. Couple is generally two equal and opposite force. We can say if the distance between these two forces is D, let this is your P, this is also P. So, this two equal and opposite force distance between D, this create a couple. So, this couple is what? This couple is represented as M. Let us we are representing this in M. So, this M will be your P magnitude of this force into distance between this perpendicular distance between these two force. So, here the perpendicular distance between two forces is P. This is very well known to you. So, that things also here we are applying. So, this equal and opposite force, this opposite force and this force generally create a couple. This couple will be what? This couple, and let the distance between this one point and externally loaded point is D. Okay. So, these things here I am drawing, then it will be more clear to you. So, let this is P. So, we want to shift this force here at a distance let D1, where we want to shift this force P. So, we shift this force from initial position, let this is 1. So, we shift this force to second position. So, as in second position there is no force, that is why we apply another opposite force here, this also similar to P. So, if we just take the resultant in position 2, the resultant force in position 2 will be 0. Now, by using this second opposite force and this initial force at position 1, as this is equal and opposite and there is a distance between these two force, that is D1. So, this force and this force will create a moment, or you can say couple. So, if we just replace this thing, like this, so this figure we can represent in the following way. So, here this force will be there and due to this opposite force and initial force will create a couple. This couple will be how? This couple will be a clockwise couple. Let this couple is M. So, here M will be how much? M will be your this magnitude of force P and the distance between two equal and opposite force, that is d1. So, this is called principle of applied mechanics. So, principle of applied mechanics tells the eccentric force P can be replaced by an equal and similarly directed force P acting through the center of gravity G along with a couple. This couple will be what? This couple will be your M is equal to your P into E. What we did here? Here you see. So, initially there was a force here, there was a force here. So, this force, similar force we applied here at G, here you can see in this figure B. So, as this G there is no externally load or externally force, that is why we apply another force P which is opposite direction. Now, this initial force P and this final force, this opposite force P, this will create a couple. This couple will be what? This couple will be, let this distance is E is given. So, this couple will be this equal and opposite force, and distance between this perpendicular distance between these two force will give a couple. So, this couple is what? This M is equal to your, you can say P into E, which I am showing here. So, instead of showing this opposite force and this initial force, here we are representing this thing in terms of M, which is actually what? P into E. So, after that actually I divide this force couple system. One is only force system and a couple system. Here you see. So, this force couple system separately we can represent, which is subjected to a force P and which is subjected to a couple M. That means, here by principle of superposition here we can say. Okay. In same location there is a force P and there is a couple M. So, what is this magnitude of this couple M? So, magnitude of this couple M is equal to your P into E, and its direction generally depends on the direction of load. Actually, here we are taking the moment with respect to G. Here these things, so here we are taking the moment with respect to G. So, once we take moment with respect to G, so then the couple will be generally clockwise in nature. That is why here we have represented this thing in clockwise direction, that you can say. So, the effect of this force P and the couple now we will treat it separately, which you can see in figure C and D. Now, depending upon this externally load P at G and this couple M, it will create some shear stress. Generally, how this shear stress is come into picture, that I will now shown in the next slide. So, you see there is a directed force, this directed force which is passing through G in figure A here I am showing. Okay. This directed force generally it will create a shear stress over every weld. What I am telling, understand, whatever the weld will be there, over every weld it will create a shear stress, because here always keep this thing in mind, what should be the direction of shear stress? The direction of shear stress is opposite to the direction of externally applied load. You see here the externally applied load at G is P, which is downward direction. Now, what is the definition of stress we know? The definition of stress we know, generally to resist this externally applied load, what is the resisting force developed? That resisting force per unit cross sectional area is called stress. So, here inside the weld, let this is weld 1, this is weld 2. So, in this weld 1 and 2, if the load is downward direction, so weld 1 and 2 the load the stress which will develop or the resisting force which will develop in weld 1 and 2, which will be opposite to that loading direction. That is why here I am representing the stress which is equal to, here this tau 1, you can say primary stress tau 1 will be equal to your what? Will be equal to your P by all cross sectional area of all weld. So, here two weld are there with equal cross sectional area. So, that is why you can say A plus A. So, here the tau 1 will be P by 2A, you can say here. So, here due to this externally applied load, whatever the resisting force developed inside the weld, so in over there in throat area, because this area here, whatever the area here we are considering, always you should keep it in mind, this area is equal to throat area, because we know throat area is the minimum cross sectional area, where if the cross sectional area will be minimum, there the stress magnitude will be maximum, you can say. Why? Stress magnitude will be maximum, because we know stress equal to, stress is equal to load by cross sectional area. That means load by cross sectional area. We are dividing this load by cross section. So, if cross sectional area will be less, stress will be high. So, if stress will be high, chances of more stress generation over there, and chances of failure also in maximum stress location. That is why here we should consider the cross sectional area for calculation is equal to your throat cross sectional area. So, here tau 1 equal to what? Tau 1 will be your primary shear stress. So, primary shear stress is what? Primary shear stress equal to your this load P, externally applied load, divided by all cross sectional area of wall weld. The wall welds cross sectional area, you can say. So, here we are considering 2 weld. So, this 2 weld cross sectional area is how much? T into L, because here length of the weld, let L, and your throat thickness, let us here we are considering T. So, this is one weld cross sectional area, and this is another weld cross sectional area. So, this is the primary shear stress. So, what is primary shear stress? So, the force P acting through the center of gravity causes direct shear stress. Here you can see in the weld, this direct shear stress is called primary shear stress. Okay. So, this primary shear stress which is representing here I am by equation number 1, you can see. So, here always you should keep it in mind, whatever the area here we are considering, this capital A is the area of wall welds. So, it is the area of wall weld. So, you can say this is A1 plus A2. So, as this area is same, this area is same. So, we can say let us this one weld cross sectional area I am representing in terms of what it is called a small a. Here instead of this, if I represent this thing in a small a, sorry, we can say P by 2a, okay, because here A1 equal to A2, here A1 equal to A2, let us this is equal to A, this also we know is same here L into T, that is why I am representing this thing. Now, we will discuss about what is secondary shear stress. The secondary shear stress generally will develop due to this couple M, this whatever the second terms we shown there, due to what replacement of what it is called, due to shifting of load from O to G, we know in G there is developed on direct force P and there is developed a couple M. So, this couple also generally developed a shear stress. So, how this is coming? So, this couple which is develop a shear stress, this is called secondary shear stress. This secondary shear stress we can represent in terms of MR by J, which I am showing here by equation number 2. How this is coming? Little bit I am explaining here, then it will be more clear to you. We know from the theory of torsion, or you can say torsion of a circular shaft, that theory also you can say. From there what we know? We know this M by J, we know this this is a shaft, okay, this is a shaft which is subjected to a couple M here. So, if it is subjected to couple M, then from there we can get some relationship between shear stress due to this couple as well as due to this twisting of this shaft. Generally there is some relationship, that is called theory of torsion. What is this theory of torsion, or you can say theory of pure torsion? From their theory what we know? That we know that M by J, J is called polar moment of inertia of this shaft cross sectional area, M by J equal to your shear stress tau by generally what it is called tau by R equal to your g theta by L. This is very common relationship. So, I am not going to drive this relationship here. So, from here what we can get? We can get a relationship that is called m by j is equal to tau by r. From these two initial terms we can get these things. So, here we can write tau is equal to m r by j. This relationship is very well known to you. So, these things only here I am representing in equation 2. That means, this secondary shear stress which you can represent in tau 2. So, tau 2 equal to here m r by j. So, this what is this m? M is the couple acting over every weld, okay, and here r is the distance from this G to this welding, you can say welding center line, you can say. So, r is the distance. So, here one thing you can see that this tau 2 is proportional to the distance r, okay. This proportional to the distance from this r is the distance from G. What is J? Here generally this J is called polar moment of inertia, polar moment of inertia. So, in this case, in this welding design case, here we should consider polar moment of inertia of each weld, because here we are interested to find out the shear stress in weld. So, that is why you have to find out the polar moment of inertia of every weld. So, here the two weld are there. So, let us here one weld have polar moment inertia is J1, another weld has polar moment of inertia is J2. So, here we should consider this polar moment of inertia in this case is J1 plus J2. So, I will explain how to find out the polar moment of inertia of this weld in detail in subsequent slide. And you know what is this G? G is called shear modulus, or you can say it is called modulus of rigidity. What is theta? Theta is called generally twisting angle due to the once this shaft subjected to some couple M, then what happens? What is the twisting occur in this what it is called in this shaft or object, that is called twisting angle theta, and here L is the length of this what is called length of this shaft. But here we are not considering this g theta by L, here we are interested to find out shear stress, we are not interested to find out twisting angle. That is why here we are considering this first two term, here you can see this first two terms we are considering. So, now we will discuss in details how to find out this polar moment of inertia of wall weld. So, here whatever the tau 2 we got, so tau 2 for this weld, that means secondary shear stress is equal to this moment or couple developed due to shifting of load from eccentric position to G into R is the distance at which location we are interested to find out this R, and divided by J. J is the polar moment of inertia of wall weld. Here two weld are there, that is why J1 plus J2. Okay, this you should keep it in mind. Now, what is this R? So, what we got here, we got a very interesting idea here. This tau 2 is proportional to which I have written is R. So, here we have to find out the shear stress, secondary shear stress in such a position where there will develop maximum secondary shear stress. So, in this case also you can see, in this case where will be the maximum shear stress with respect to G of this weld. So, we know the distance, farthest distance of this G to weld is the corner point of this weld, this I am representing in terms of A. So, let the distance here is this distance. So, this is the maximum distance, you can say R max. So, we should consider this R distance for designing this types of problem is that point which is the farthest distance from the G of weld. This you should keep it in mind. So, here the farthest distance is A. So, that is why we consider that R max in this analysis. So, here we should consider tau 2 equal to tau 2 max will be your, you can say m into R max divided by J. This also you should keep it in mind. So, for finding out tau 2, we should consider the farthest distance of the weld from G. Now, what should be the direction of this tau 2? the direction of this tau 2, you see it should be always tangent to this, called tangent to this twisting or rotational couple, you can say. So, you see in this furthest distance what happens here, that things you can represent if you draw a straight line from G to A, perpendicular to that generally will be the direction of tau 2. Now, this tau 2, what should be the direction, whether it is anti-clockwise or clockwise direction, that also you should know. So, here the direction generally, this whatever the couple we will apply, this couple generally developed a resisting couple inside the weld. So, whatever the applied couple will be there, the direction, the resisting couple inside the weld will be opposite to that, what I am telling, understand. That is why here you can see, as the direction of couple here is G is clockwise. So, opposite direction generally in weld A, this tau 2 direction is opposite to this couple M. So, if it is clockwise, there the direction will be opposite direction, and this direction at this A location will be the tangent of that point, tangent of this point, in the sense you can say the tangent means if we draw this G in G and A. So, tangent will be this generally here, this is G A equal to R max. So, this will be generally this radial distance perpendicular direction. This is very well known to you. So, that is why this tau 2 direction should be like this. So, one thing here you should keep it in mind, whatever the stress developed inside the weld, this is direction should be always opposite to the direction of applied force and applied moment. That is why here I am representing tau 2 as like this, you can see in figure B, what I am telling you, understand. Now, we will show you how to find out the what it is called polar moment of inertia. So, to find out polar moment of inertia, let us consider. So, here I will show you how to find out polar moment of inertia of a weld. So, to find out polar moment of inertia, we know polar moment of inertia is represented in terms of J. So, J equal to Ixx plus Iyy. This is very well known to you. So, polar moment of inertia is second moment of inertia about x axis plus second moment of inertia about y axis, which is very well familiar to you. So, I am not going in details here. So, we have to find out the polar moment of inertia of each weld with respect to what? With respect to center of gravity G. So, let this is the weld, this is one weld W. So, here we are considering this weld throat thickness here. So, where weld throat thickness is T let. Now, here this is the G, we know, we have already find out G. Now, let us consider the G of this weld whose length is L, so, here this G of this weld which I am representing here, let us G1, okay, G1. So, this weld wound CG, so the weld wound CG I am representing in terms of G1, let this is weld 1 W1, okay. Now, so first of all we have to find out the Ixx and Iyy, because first of all we will find out the polar moment of inertia with respect to G1. So, we will just show, so here I am just finding out G1, that polar moment of inertia is equal to polar moment of inertia I am writing about weld CG. Let this weld CG I am representing is here you see G1. So, weld CG here that is G1 position, okay. That things here I am writing. So, here we know, here generally there will be Ixx plus Iyy. So, let this is our x axis and let this is our y axis. So, about x axis and y axis, so Ixx we know here what we know, Ixx is equal to, we know as Ixx generally once we go for finding out. So, how to find out the moment of inertia? Let this is a rectangular cross section, let its breadth is b and height is let h. Now, let this is our x axis and this is our y axis. Now, we know once we generally find out the moment of inertia with respect to x, that we generally represented as Ixx. So, moment of inertia with respect to second moment of inertia, you can say with respect to x is represented as Ixx. So, Ixx equal to, generally how to find out these things? We generally used to take a small stiff which is parallel to this x axis. Here we are taking, let this a small stiff thickness is dy and this is breadth is given, this breadth is given b. So, we know Ixx equal to your, and distance from this dy to this is y. So, we know generally to find out the Ixx, we have to integrate, so integrate minus h by 2 to h by 2 with respect to y axis, if it will be y square, this a small area of this stiff dA. Okay. So, this we can say minus h by 2 to h by 2. Okay. So, y square, here dA we can represent as b into dy, because dA is the cross sectional area of this small stiff dA. So, its length is given as b and a small stiff thickness is dy. So, that is why b dy we can say. So, here we can write as b into y cube by 3, okay, minus h by 2 to h by 2, correct. So, we can say b h cube divided by 12. If you just calculate this thing, this you can say. So, once you go for finding out Ixx, here always keep this thing in mind. For Ixx, generally there will be this x dimension, or x is single order and its y dimension is third order. So, here Ixx will be what? Ixx will be your L, here this other direction is T throat thickness. So, TQ divided by 12. Similarly, we can find out what is Iyy. So, in case of Iyy, y dimension will be single order. So, you can say T LQ divided by 12, correct. Now, here as this T is comparatively very small, T is comparatively very small than L. So, what we can say for calculation of this polar moment of inertia, we can write as this is approximately equal to your Iyy. Here we are neglecting, because this LTQ term generally is much lesser than Iyy. So, that is why we can say this Jg1 equal to your Iyy itself. We are just generally just neglecting this Ixx term. This you should keep it in mind. Okay. So, what is Jg1? So, the polar moment of inertia about its own CG is Iyy. This equal to your what Iyy, what we got? Iyy we got as L TLQ divided by 12. So, here we can write T into L into L square divided by 12. So, T into L is the cross sectional area of one weld, which I have already told you. Let this cross sectional area of this weld is equal to a small a is equal to T into L, which I am representing. So, A L square by 12, this you can say. So, this is the polar moment of inertia about its own G. Now, we are interested to find out the moment of inertia of each weld with respect to overall G, this G. Okay. So, here now to find out the polar moment of inertia with respect to this what it is called, with respect to this G, about this G, what are the things required to do? We have to use parallel. So, polar moment of inertia, now we will just find out polar moment of inertia about overall G, here I am writing overall CG of welds, that is G, is I am representing as JG. So, what will be the JG? So, there to find out this JG, we will use parallel axis theorem. What it is called? Moment of inertia, here we will use parallel axis theorem. So, what is parallel axis theorem? Which is very well familiar to you. So, parallel axis theorem is tell we know that its moment of polar moment of inertia about its own G, that is Jg1, plus always you should keep it in mind distance from this G to G1, distance from this G to G1, let this distance from this G to G1 is R1 I am representing. So, here generally this polar moment of inertia will be your Jg1 into area of that weld, area of this weld to distance from this G to G1. See, here one thing you should keep it in mind. What is this R1? R1 is equal to distance between G, G1. What I am telling, understand? This you should keep it in mind. So, so we can easily find out what is the polar moment of inertia of this weld 1. So, polar moment of inertia of this weld 1 we can say Jg. So, this Jg, this I am representing as overall, as it is overall. So, as it is fast weld, we can represent it as J1. What I am telling, understand? Let us see, I am representing this thing in J1. So, Jg will be how much? So, Jg we can say Jg1 already I have find out what is Jg1. Jg1 let us I am representing from equation 1 we can say. So, Jg1 we have already got A L square by 12. So, this is Jg1. So, and A into R1 square also is known to us. So, you can say this is the polar moment of inertia into area of that weld, L square by 12 plus Rn square. This you should keep it in mind. So, how to find out this polar moment of inertia of weld 1, or you can say this is this also you can say here I am representing J1, let us J1 equal to Jg of that fast weld, okay, of this one weld. Now, here as there is two weld of equal length, so here also this way we can find out the other weld polar moment of inertia also. So, other weld polar moment of inertia let us J2. So, here to get tau 2, we know there is a relationship, that is your MR max divided by, because we have to consider maximum shear stress. So, MR max by J. So, here this J will be what? J will be your this J1 plus other weld J2. So, this way, so fast weld polar moment of inertia already I find out this. So, J2 also we can easily find out, by this way we can easily find out what is the tau. So, we got what is tau 1 and tau 2. So, by using this tau 1 and tau 2 we can find out the resultant component of this overall shear stress. So, how to find out the resultant component of overall shear stress, that I am now going to show you. So, what we got? We got that this is a weld. So, in this weld, due to the primary shear stress, in every point there is a primary shear stress tau 1, which is we consider as uniformly distributed over the weld throat. So, these are all tau 1, these are all tau 1 shear stress. This tau 1 is coming due to what? So, tau 1 is coming due to your externally applied load by all cross sectional area. See, so this capital A is cross sectional area of all weld, this you should keep it in mind. So, this here you can say A plus A as there is two welds. So, A plus A will be the capital area. Now, with respect to G, what we have seen with respect to G, here the farthest distance is generally A distance, I have already told you. this furthest distance of the weld is A distance. So, this is the, you can say, R max. So, in this R max, what should be the direction of this tau 2? So, direction of this tau 2, here we have already observed the direction of moment generally clockwise in nature. So, inside the well the direction of resisting moment will be opposite to this. So, along that direction generally the shear stress will act, which will be generally tangent to that point, generally which is the perpendicular direction of that radial distance r1. So, here generally this tau 2 will be opposite to this. This is the tau 2 perpendicular to this radius r max, and whose direction is opposite to the moment direction m. Now, here this tau 1 and tau 2 in this location is known to us. So, tau 1 also tau 2 is also, we got tau 2 equal to your, we know as m r max divided by j. So, this you can say tau 2 here, instead of writing max, here I am writing just tau 2 only. Okay. Now, let the distance between these two, the angle between this tau 1 and tau 2 is theta. So, by vector addition we can easily find out what is the resultant component of, what is called resultant component of this tau 1 and tau 2. So, resultant shear stress, so what should be the resultant shear stress? So, resultant shear stress tau r we can easily find out by either vector addition of that is triangular law, or we can use here parallelogram theorem also. Let this is our tau 1, and let us another force component is here tau 2. This is our tau 2. So, let the angle between this is theta. So, we can easily find out what is the resultant of this tau 1 and tau 2. We know this is the formula as tau 1 square plus tau 2 square plus 2 into tau 1 tau 2 cos theta. This is very well a standard relationship. I am not going to derive this thing because this is very simple things. You can get this parallelogram law. So, by using these things you can easily find out. So, this is the resultant shear stress in your weld, that you can say this is the maximum resultant shear stress, you can say this is the tau r maximum which is developing generally inside the weld. This tau max should be equal to our permissible shear stress. So, once we equate this tau r with permissible shear stress, then generally from there we can easily find out what is the throat thickness T, because you know this tau 1, tau 2 which is a function of what? Which is a function of throat thickness T. So, once we know this throat thickness T, then we can easily find out what is the leg length. So, leg length we know, T by leg length is generally considered as what it is called cos theta, cos 45 degree you can say. Okay. So, here you can easily find out H will be your T by you can say 0.707. Okay. So, by this you can easily find out what is the leg length also, leg length of this weld. So, this is your throat thickness and leg length. So, this is the design throat thickness and design leg length. So, once a welded structure you can say subjected to some eccentric types of loading. So, beforehand we should calculate what should be this welding dimension. That means, after that generally we have to go for doing welding, where we have to develop this much of throat thickness weld, or you can say leg length weld, then our structure will be safe. So, next class I will start from here. I will solve some problem on this eccentric loading types of welded structure. Okay. After that I will discuss about some other static analysis related welded joint. Okay. Thank you.